Hi and welcome to this video on polar coordinates and Moivre's theorem. This video is primarily aimed at students revising for their A-level maths and or further maths exam, as well as students who are preparing for or partaking in a STEM-based degree. If this is the first video from my collection that you are watching, you may want to take some time to watch my introductory video. This should give you a better idea of how to get the most out of these videos. Up until now, we have used the Cartesian coordinate system. Polar coordinates, r and theta, are used as an alternative method of describing location to Cartesian coordinates. Polar coordinates relate to the angle from the initial line, being the positive x-axis, and the distance from the origin. Visually, if we have here the origin, and we're interested in the location of some point P, and this is the x-axis. Then we could describe this using x and y by saying we go long x and up y, or we could describe it using polar coordinates, r and theta. R is the distance from the origin, whilst theta is the angle from the positive x-axis. Here, using trigonometry, we can see that x equals r cos theta and y equals r sin theta and theta equals tan to the minus 1 of y over x. In summary, if the Cartesian coordinates and the polar coordinates of a point are x, y and r and theta respectively, then x equals r cos theta, y equals r sin theta, r equals the square root of x squared plus y squared. Therefore, cos of theta equals r divided by the square root of x squared plus y squared, and sine of theta equals y divided by the square root of r squared plus y squared, except at 0. Knowledge of this helps to convert from polar coordinates to Cartesian coordinates and vice versa. We can also sketch polar graphs. For this, you first of all need a polar coordinate grid. This consists of a series of circles extending out from the pole. The pole is what we would call the origin in a regular coordinate system. The grid then has 5 different lines passing through the pole. Each represents a different angle of which exact values are known for the trigonometric functions. Here is an example of what a polar coordinate grid looks like. Below I will include the basic shape of some common polar graphs. I will not draw them onto polar coordinate grids, instead I will just provide basic shapes on basic rectangular coordinate grids. Let's start with r equals sine theta. An easy way of plotting polar graphs is by looking at what value r takes at each of the angles depicted by the lines in the polar graphs. Doing so gives us this shape for r equals sine theta. Moving on to r cos theta, then we get this shape. R sin 2 theta and r sin 3 theta give these two shapes respectively, whilst r equals cos 2 theta and r equals cos 3 theta give the following shapes. We will now move on to look at maximum and minimum values of r. For simple equations involving only cos theta or sin theta, using knowledge of the maximum and minimum values of sin theta and cos theta you can work out the maximum and minimum values of r. So let's look at an example. If you were given r equals 2 plus cos theta, we know that the maximum value of cos theta is 1, and we know that the minimum value of cos theta is minus 1. Subbing this into our equation for r, we know that the max value of r is 3, whilst the minimum value of r is 1. Alternatively, we could write this as minus 1 is less than or equal to cos of theta, which is less than or equal to 1, which implies that 1 is less than or equal to 2 plus cos theta, which is less than or equal to 3. In more complicated cases, when the equation is of the form r equals f of theta, you could differentiate f of theta, and setting this equal to 0 and solving will give the values of theta for which r is at its maximum and minimum. So let's try this for the same example. So we had r equals 2 plus cos theta, which is our f of theta. So if we then differentiate this, get f dash of theta is equal to minus sine of theta, setting this equal to 0. And solving tells us that we get our maximum and minimum values when theta equals 0, pi, 2 pi, etc. So then let's look at cos theta at these values. So when theta equals 0 or 2 pi or 4 pi, etc., cos theta is 1, and when theta equals pi, 3 pi, and so on, cos theta is minus 1. So we know these are the maximum and minimum of cos of theta, so we can sub these in to our equation of r to get that the maximum of r is 3 and the minimum of r is 1, which is the same as before. Complex numbers can also be written in polar form. Consider z equal to x plus yi. Then the modulus of z is the square root of x squared plus y squared, and the argument of z is theta. As we know that x equals r cos theta and y equals sine theta, this implies that z equals r times cos theta plus I sine theta, where r equals the modulus of z, which is greater than 0, which is the modulus, and theta is the argument of z, with minus pi less than theta, which is less than or equal to pi. There are rules for both multiplication and division when it comes to complex numbers in polar form. For multiplication, if you have two complex numbers, s and t, the modulus of st equals the modulus of s times the modulus of t, whilst the argument of s times t equals the argument of s plus the argument of t plus k times 2 pi, where k is either minus 1, 0 or 1. The argument is in the interval minus pi to pi. For dividing in polar form, the modulus of s divided by t equals the modulus of s divided by the modulus of t, whilst the argument of s over t is the argument of s minus the argument of t plus k times 2 pi, where again k is either minus 1, 0 or 1, so that the argument is in the interval between minus pi and pi. The square roots of a complex number, s, have modulus the square root of modulus of s, and arguments of a half of the argument of s, and a half of the argument of s plus or minus pi, depending on whether the argument of s was positive or negative. If theta is a real number, e to the theta I is defined as e to the theta I equals cos of theta plus I sine theta. This means that the polar form of a complex number, z equal to r times cos of theta plus I sine theta, can be written as z equals r times e to the I theta, where r is greater than 0 and theta is in the interval minus pi to pi. Note that this gives meaning to the famous equation known as Euler's identity, e to I pi plus 1 equals 0. From the equality at the top of your screen, we know that e to the power of pi I equals cos of pi plus I times sine of pi. Cos of pi being minus 1 and sine of pi being 0. This means that we have e to the power of pi I equals minus 1 plus 0 times I. So we have e to the pi I equals minus 1, and then a simple rearrangement tells us that we have e to the power of pi I plus 1 equals 0, Euler's identity. Moving on to have a look at an overview of the basics of de Moivre's theorem. For n in the integers, trigonometrically, it states that cos theta plus I sine theta all to the power of n equals cos of n theta plus I times sine of n theta. Whilst exponentially, it states that e to the theta I all to the power of n is equal to e to the power of n theta I. So let's move on to look at some examples which use polar coordinates and de Moivre's theorem. First example, we want to simplify. Cos of pi over 3 plus I times sine of pi over 3 all to the power of 5 divided by cos of pi divided by 3 minus I times sine of pi divided by 3 all to the power of 4. So we can use de Moivre's theorem to move the power of the numerator inside the brackets. So we get that this is the same as cos of 5 pi over 3 plus I sine of 5 pi over 3 all divided by. Now here we want to be able to apply de Moivre's theorem, but we can't because this has got a minus I sine. So as cos is symmetric and sine is an odd function, we can say that this is actually equivalent to cos of minus pi over 3 plus I sine of minus pi over 3 all to the power of 4. Now we can apply de Moivre's theorem, but count this as a minus 4 so that we can move it up into the numerator. So we'd get cos of 5 pi over 3 plus I sine of 5 pi over 3 multiplied by cos of 4 pi over 3 plus I sine of 4 pi over 3. By using the rules of multiplying two complex numbers which are in polar form from earlier, we know that this is the same as cos of 9 pi over 3 as we just add the arguments. So plus I sine of 9 pi over 3, and obviously 9 pi over 3 is equivalent to 3 pi. So we get cos of 3 pi plus I sine of 3 pi. And cos of 3 pi is minus 1. And sine of 3 pi is 0. So our actual solution is just minus 1. Moving on to a second example. We want to simplify one minus I to the power of 10. We know that this can be written in the form of a polar complex number of r times cos theta plus I sine theta all to the power of 10. But we need to work out what r and theta are. So we know that r is the square root of x squared plus y squared if we have a complex number of the form z equals x plus iy. So here we have it being the square root of 1 squared plus 1 squared, which is simply root 2. And we know that theta is tan to the minus 1 of y over x, which in this case is tan to the minus 1 of minus 1, which is equal to minus pi over 4. So now that we can rewrite 1 minus I to the power of 10 in the form of a polar complex number, we get that it is root 2 multiplied by cos of minus pi over 4 plus I sine of minus pi over 4 all to the power of 10. Then using Moivre's theorem we can bring this 10 down into the argument and also do the square root of 2 to the power of 10. So we get that this is actually 32 times cos of minus 5 pi over 2 plus I sine minus 5 pi over 2. And then cos of minus 5 pi over 2 is 0. And sine of minus 5 pi over 2 is minus 1, which gives us a final answer of minus 32i. Moving on to a further example that you can have a go at your. I will not go through the answer. Instead, after writing the question, there will be a 5-second countdown before the answer is revealed. Question 1. We want to simplify 2 plus 2 root 3i all to the power of 6. 5, 4, 3, 2, 1. So the answer here was 4090. Now let's move on to look at more of de Moivre. So de Moivre's theorem can help us to realise that cos of n theta is actually equal to the real part of cos theta plus I sine theta to the power of n, whilst sine of n theta is actually equal to the imaginary part of cos theta plus I sine theta all to the power of n. This means that we can find alternative ways of writing cos n theta and sine n theta, which allow us to integrate powers of sines and cosines more easily. To find these, we need to expand cos theta plus I sine theta all to the power of n using the binomial expansion. We'll get a mix of cosine and sine terms and a mix of real and imaginary terms. Equate the real terms and this will give you cos n theta, and equate the imaginary terms and this will give you sine n theta. So let's do an example. We want to find out another way of writing cos of 6 theta. We know that this equals the real part of cos theta plus I sine theta to the power of 6. We now need to expand this using the binomial expansion. For the next line, I will not write out cos and sine theta fully. Instead, I will write a C for cos theta and an S for sine theta, just to make things simpler. So this equals the real part of, so using the binomial expansion, we get that it's cos theta to the power of 6 plus 6 times cos theta to the power of 5 times I sine theta minus 15 times cos theta to the power of 4 times sine theta squared. So minus, because I squared is equal to minus 1, minus 20 times cos theta cubed times I times sine theta cubed. Again, it's a minus because we have I squared equals minus 1, and then times the I because we've got I cubed here, plus 15 cos theta squared sine theta to the power of 4. We'd have I to the power of 4 here, which is just 1, plus 6 times cos theta times I times sine theta to the power of 5 minus sine theta to the power of 6. So now we're only interested in the real part, so this is just cos theta to the power of 6 minus 15 cos theta to the power of 4 times sine theta squared plus 15 cos squared theta times sine theta to the power of 4 minus sine theta to the power of 6. And this is our final answer. Thank you for watching this video.